Louder now than it would. Yeah, I'm set to go. Should we wait for Fauzi? Okay, sorry for the delay in starting. It's already 10 minutes past 10. That's well, you saw there that the standard camera guy is not there. So welcome today to the fifth and last lecture of the cosmology lectures that I'm giving here. And today I will talk about the polarization of the cosmic microwave background. And I will actually not talk about other themes, but I will summarize what you've heard in the all 5 lectures together. And then I hope that at the end of this lecture today, I have given you the tools that I can give you to use the cosmos as a physics laboratory and to use the universe as a means to constrain particle physics and gravitational physics. So today I will talk about the polarization of the cosmic microwave background, but before we go through all that, I will first remind you of what I have told you before about the cosmic microwave background, the temperature and anisotropies. And then I will briefly refresh your memory about the polarization of radiation, how that works and how it comes about from scattering. And then I will go through the different types of polarization that you can recognize in the cosmic microwave background. And then I will focus on the modes that could be the smoking gun of inflation, but that can also be produced by other foreground effects. And then I will apply that and show you the latest results of the BICEP Keck Planck combined analysis of the CMB B-mode polarization. So first the teaser about the polarization that I'll be talking about later before I remind you of the CMB. The fact that every photon has an orientation. So an individual photon already has an orientation. It has a direction of the E of the electric field and it has a direction of the magnetic field. So for a single photon there is always an orientation and it makes no sense to speak of polarization. But if you have a large flux of radiation and it's a fluid, then of course the collection of photons can be randomly oriented or can have preferred direction of orientation, so it can be partially polarized, which says that a fraction has the same orientation that's not random, or it can be fully polarized, etc. But before it makes sense to talk about that, let me remind you what we do to study the cosmic microwave background. So we observe the temperature of the cosmic microwave background radiation in a direction of a function of 2 angles, phi and theta. The scalar function of phi and theta can be expanded in spherical harmonics. These are the spherical harmonics, the eigenfunctions on a sphere, the eigenfunctions of the Laplacian on a sphere. These are the coefficients, the ALM. The ALM, of course, can be obtained by taking the inner product of your temperature map with the spherical harmonics. And then if you sum out the M component, which M is like a directional index, whereas L is a scale index, the scale on which you see anisotropies in spherical harmonics. If you sum over the directions, then you get the total power of anisotropy at a particular scale of multiple L. You apply that to the cosmic microwave background map and you get this figure. So the power in multiple L's is here given on the vertical axis as a function of the multiples on the horizontal axis. And you see this very clear oscillatory shape of the power spectrum of the cosmic microwave background. And so now the point is that this is, so far it's only a Fourier transform and sum over modes. It tells you how much power is in there. But this is related to the correlations in the initial conditions that give rise to this perturbation spectrum. Because if the cosmic microwave background comes from a Gaussian random field, and you could measure infinitely many universes, then for each choice of L and M, and another choice of L prime and N prime, you can compute the 2-point correlator in spherical harmonic space. So if you had infinitely many universes, and I take A1 naught and A1 naught, and I multiply it for each of these universes, and I take the average, then I find that this converges to some number, which is the variance of A1 naught. And for L or M not equal to L prime or M prime, I will get a zero correlation. But if we have only one universe, I multiply ALM with AL prime, M prime on the same map, this will be some finite number, because I only have one universe. But if it's from a Gaussian random field, then even for one universe, if I take this sum over M, I end up with a quantity that only depends on L. And you notice that this correlator, in fact, only depends on L. So for each M, the variance will be the same, given some value of multiple L. So if I compute this power statistic, sum over all M, then for the larger values of L, this power statistic dl actually measures a large ensemble of random variables that are drawn from the same distribution with the same variance CL. But this is only true if it is a Gaussian random field that gives rise to the CMB perturbations. So fundamentally we only have access to this quantity dl, which is the sum over the ALM, and that doesn't guarantee that the origin is a Gaussian random field, but if it is a Gaussian random field, then dl is a very good probe of the variances in the Gaussian random field as a function of multiple L. So dl measures two L plus 1 independent random variables drawn from the same Gaussian distribution with variance CL. So that is about the statistics of the cosmic microwave background. Then the question was, how do you compute this cosmic microwave background from your theory? What is the prediction of cosmological theory to get to this temperature spectrum? The theory is given by the equation that's first written down by Sachs and Wolf. So it's the Sachs-Wolf equation. The temperature perturbation in some direction, n, is given in a gauge invariant notation by the density of photons, the relative velocity of that spot on the surface of last scattering compared to the velocity of the observer, and the gravitational potential on the surface of last scattering, plus the integral over time of the time derivative of the gravitational potential along the photon path. This is the integrated Sachs-Wolf effect. So the photon travels from the surface of last scattering towards us. It falls in some potential along the way and it climbs out of it again. If there was no change in the potential, the net effect on the energy of the photon is zero. However, if the potential in the meantime changes of depth, becomes deeper or less deep, then the photon will gain or will lose or gain energy while traveling through that potential. So, at first order, this is the equation that describes the temperature of photons that we observe. Photon density, the velocity, which is negligible, the gravitational potential, and the time change of the gravitational potential along the photon path. If perturbations are adiabatic, which means that at the initial conditions, at the end of inflation, the perturbations laid out in the universe are the same in all fluids that you have. So dark matter, photons, and baryons have overdensities in the same places and have underdensities in the same places. Then there is, of course, since the perturbations in all fluids are the same, there is a direct relation between the photon density and the gravitational potential. This relation can be computed. You can compute it if you write down the Boltzmann equations. The velocity term remains negligible, and then the sum of these three terms amounts to 1/3 psi. One other ingredient that goes into this summation is the fact that for perfect fluids, psi is equal to minus phi. So here you have 2 psi. So for adiabatic perturbations, the temperature at a spot on the surface of last scattering, focusing on this term only, is given by 1/3 times the gravitational potential. And here is the interesting feature that I asked you to remember when we discussed this. When you look at a cold spot in the CMB, you are looking at an overdensity. Because the gravitational potential in the overdensity is deeper, and gravity wins from the other contribution, which comes from the high photon density. So the gas there is hot, but the potential is so deep that the photon comes out relatively cold. When you look at a hotspot, you're looking at an underdensity. The photon density is not so high, so the gas is not really hot. But the fact that it's underdense means that the photon comes down from gravitational hill and gains energy. So this is hopefully what you remember from that course. So gravity wins. Hot is underdense, cold is overdense. And then if you do the computation carefully, you can compute this green line if you put in the ingredients that we think we have now in the universe, and you see that it fits the data points perfectly well. So the ingredients that go into computing this green line, which is the prediction of the spectrum of temperature anisotropies in the CMB, are some initial spectrum of perturbations, which is close to scale invariant. So you have an amplitude and a scale dependence of the perturbations. To construct this line, you need to put in a relative density of dark matter, a relative density of baryons, because if you have more or less baryons, that changes the ratios of the even and odd peaks, as you may remember. If you change the amount of dark matter, you change the depth of the peaks. A fifth ingredient is the age of the universe. If the universe happens to be very young, the surface of glass scattering would be nearby us, so we would observe things on different angular scales than when the universe is old and the surface of glass scattering is very far away. If it's far away, if the universe is older, these peaks will move to smaller scales, simply because you put it far away. Right. There's one contribution that that you did not see in the previous slides, but we did discuss, and that is the fact that so far I've only discussed scalar perturbations, anisotropies that come from the gravitational potential, which itself is sourced by scalar perturbations from the densities of the different fluids. But in general relativity you can also have tensor perturbations in a metric, and they also give rise to temperature correlations in the cosmic microwave background. So the scalar perturbations give this nice oscillatory feature, but the tensor perturbations give a different shape in the temperature perturbations. The tensor perturbations give different shape. But remember that the scaling of the axes is different by an order of magnitude. So the tensors, if you would plot them inside this plot, would actually add a contribution that stays below this line, and only on very large scales possibly changes the temperature correlations. And it used to be actually this effect that gives the tightest constraint on the presence of tensor perturbations in the cosmic microwave background. This sets some upper bound on the presence of tensors, but no lower bounds. You can replace scalar perturbations with tensor perturbations at this end of the temperature spectrum of the CMB. Okay, so this is a very brief summary of the cosmic microwave background lecture of 2 lectures ago. Is there a question?
What are the lower plots?
The lower plots are the polarization, which I will talk about now. Thanks for asking. So, the cosmic microwave background in each direction has a temperature. It's a collection of fluid, of photons, and we did not yet discuss whether the orientation of the photons is random or not. If a gas is in a perfect thermal equilibrium, the photons will come out in a random orientation. Each photon has an orientation, so if you measure infinitely many photons, the average of the orientations will be the average of the orientations will be 0. They're just following the whole 2 pi circle. So unpolarized line means that individual photons have a random orientation. Polarized line means that individual photons have the same orientation. And partially polarized, of course, is then also a possibility. So how do you produce polarization, and is this a mechanism that can be present in the early universe? So I show you a number of animations that all come from the same website by Wayne Hu, who's a professor in Chicago, the Fermi Institute. So if you want to study the details of polarization a bit more, I suggest you Google for his website and go there. Light can be polarized by reflection, simply by means of symmetries and orientations. You have isotropic radiation coming in. So this cross is not an individual photon, this cross is a collection of photons. And the two axes suggest that the photons have all orientations in their collection. But by the reflection, all the orientations that are perpendicular to the surface are reflected much less efficiently. Or perhaps absorbed and then emitted as thermal radiation in a random direction. But from the original radiation that comes in on the surface, only a polarization orientation that is perpendicular to the surface, where the electric field is perpendicular to the surface, is reflected very efficiently. So by reflection, I let isotropic light, unpolarized light, fall onto the surface and let it reflect, and by reflection, I end up with polarized radiation coming out. Then, more explicitly, the effect that happens at the cosmic microwave background is Thomson scattering, which means that a photon encounters an electron and through its interaction with the electron is changed into a random direction. But you can see from this picture that the orientation of the incoming unpolarized light determines how efficient it can be reflected. The orientation that has an electric field that is perpendicular to the final direction is reflected is scattered by the Thomson scattering very efficiently. The orientation that is parallel to the direction of emission is of course very inefficient, because the electric field and the magnetic field of the photon are perpendicular to the direction of the photon. So now, if I have isotropic light coming into the photon, photons coming from this direction will be filtered into a polarized direction, but photons coming from another direction will be also filtered in the opposite polarized direction. So the resulting light coming out of this type of scattering, isotropically on the electron, will again be unpolarized. And this is why, if you have a gas in thermal equilibrium, you end up with unpolarized light, because there are photons coming in random orientations from all directions onto your electrons, and they will be scattered again in random directions with a random orientation, meaning that the net effect will be unpolarized radiation. But now imagine that the electron sees himself some anisotropy, particularly an anisotropy that is quadrupolar, which means that there is, for example, hot radiation, so more radiation coming from this direction and from the opposite vertical direction, and cold radiation coming from the horizontal direction and the opposite horizontal direction. That means that more radiation comes from the vertical directions. So after the scattering, more radiation that is polarized in the horizontal orientation is reflected by the electron. Less radiation comes from the cold direction, so less radiation parallelized in the opposite direction will be reflected by the electron in our direction. So, if the electron sees a quadrupole anisotropy that is perpendicular to the line of sight, this electron will reflect into our direction a radiation that is net polarized. Okay? So it's simply by the orientations of photons and electrons that the reflection gives polarized light. So if you have hot radiation in one direction and in the other direction of the photon, and cold radiation in the orthogonal directions, you end up with linearly polarized light. Now, we have spent a lot of time understanding how the cosmic microwave background is anisotropic. So we see it as anisotropic. And that means that also locally at the surface of last scattering, there is some degree of anisotropy. So you can search for the degree of polarization of cosmic microwave background light and put that in a map of cosmic microwave background temperature. These white lines indicate the orientation, the tendency of the orientation of the photons coming from that spot on the sky. And you see that there is a very clear polarization pattern. This is, I'm zooming in here on one particular map of one particular frequency, but of course you measure this polarization in many different frequencies when you study the cosmic microwave background. One reason is that by looking at the frequency dependence, you can filter out foregrounds that have nothing to do with cosmic microwave background. So you can construct a map of polarization of the cosmic microwave background. Now the question is, how is this related to fundamental physics? Well, what you already understand is that the polarization of each direction is dependent on the anisotropy locally. So you can understand already that by looking at the polarization of the cosmic microwave background, we have access to more information than when we only measure the anisotropies ourselves. Because by looking at the temperature of these maps, we know the anisotropy of the radiation as we receive it here. But by looking at the orientation of the photons, you have more information because you see what was the three-dimensional anisotropy that the electron that last reflected that photon towards us saw. Okay, to study the polarization, you decompose the vector field in different components. Maybe I should put this. Maybe I should put this slide later. Let me skip this first. So, once more, a repetition of the same statement that a local quadrupole, so local at the electron that scatters the radiation towards us, a local quadrupole leads to polarized radiation. So here is this is the real component of a spherical harmonic of L equal to 2, so it's a quadrupole. And if L is equal to 2, it means that you have 5 different spherical harmonics. M runs from -2 to +2. And this is the real part of the spherical harmonic for M equal to 0, so that's just a particular choice of orientation of this quadrupolar effect. If you have hot radiation here, hot radiation here, but you have cold radiation in the directions orthogonal to it in a quadrupole distribution, then the emission of the light coming from this point will be polarized. I will do that one later too, I think. No, I will not do that later. When you describe a vector map on a sphere, you need more information than just the magnitude in one direction, because you need an orientation in that direction too. In order to describe that, you can decompose the vector field in two types of orientations. Very much like electromagnetism, you can describe it in terms of one vector field that comes from the divergence of a scalar, and another vector field that comes from the rotation of a fundamental vector field. So the difference between the two is that this vector field has zero rotation, whereas this vector field has zero divergence. So these are the E and the B modes. And one characteristic difference of the two is that if you reflect this one, you put an axis on it and you flip the vector field around it, it remains the same. Whereas if you reflect the B mode polarization, then it will turn into the opposite sign radiation. It will turn in the opposite sign vector field. So the B modes are parity odd and the E modes are parity even. Decompose the vector field in the different types so that you can talk about the different components that go into the orientation of the polarization, that go into the orientation of the vector field. We've discussed this slide. But now, let's see. Let's try to understand these different modes. If you have a temperature fluid, if you have a fluid of photons with a temperature distribution, and the temperature is actually on very large scales given by these bars, saying that, for example, along this bar you have, at the dark center of the bar, you have hot gas, and on the white edge you have cold gas. So cold and underdense hot, well, you get a low temperature from here and you get a high temperature from here. So let's forget about what the temperature of the gas was, because actually it's the gravity that gives the temperature. Hot radiation coming from here, cold radiation coming from the sides of the bar. That means that on this bar, the polarization will have the orientation that points into the direction of the quadrupole, locally. And now if you repeat this bar in these different directions, then you see that at the center of this bar, you get this type of circular polarization, and at the center you get, of course, the divergence. So what this figure tries to explain, I didn't say it very clearly, but what it tries to explain is that this is all polarization, this is all a vector orientation that is of the type of the E field. So the temperature anisotropies give rise to E-type polarization. That means that if you observe the E-type polarization, and its origin is the same as the origin of the temperature perturbations, namely the surface of less scattering, then the E-type polarization must be correlated with the temperature anisotropies. This is a very important test to see whether the polarization that you're observing comes from the surface of less scattering or the polarization was imprinted on the photons at a later stage on their path towards us. So this is a very important test. The B-type polarization, which is rotated 45 degrees with respect to the E-type polarization. I didn't explain why, but please take for granted that it does. This cancels out when it comes from the scalar field. And this is as simple as saying that the temperature field is a scalar quantity. You have one value at each point in space-time. So you can construct a vector field from it, but this vector field will be rotation-free, will have no vorticity, will be curl-free. That means that you can produce E polarization, but you cannot produce B polarization because B polarization has a curl. Okay? You start with a temperature field and you let that be the only source of anisotropy, then you cannot produce a vector field that has a net vorticity at linear order.
What you want to say is just that you can do the divergence of your scalar, and then you get a vector, but you cannot do the curve.
Exactly. Well, you could take the curl of the divergence of a scalar, and then you get zero. As long as things are linear, because if you start taking squares in the scalar field, then you at second order you can produce B correlations. So then, how can you produce B modes? Well, that means that you need to put in something that is more than a scalar. For example, a fundamental vector degree of freedom at your surface of less scattering, or a tensor degree of freedom, because these have simply more values at the same point of space-time. To describe a vector, if it's a 3D vector, then at each point in space-time you have three values. So you can have a intensity and an orientation encoded in your field. So one example is gravitational waves, which are tensor modes. And here you see here you see a quadrupolar temperature anisotropy, but on top of that, it is squeezed by the vector field or the tensor field in your gravitational theory. And that means that you can add more information to the point. So this is a very, very vague description of what it does, but I hope that you buy from me that if you add more degrees of freedom, you can produce B correlations, because you simply need something more than a scalar. So for those of you that wanted to see some equations and not just fake stories, you can write down the equation of motion for the time dependence of your different types of polarization. These m's, as a function of multiple L, describe the intensity of the radiation flows, and this is the temperature anisotropy. So this is simply the time dependence of the intensity. This is a wave number k. This is some geometrical term, and you see that there is a mixing of the different L modes. And here we have the electron density, the Thomson scattering cross-section, scale factor, and again the intensity. And here is a source term. These m's in these equations, unfortunately they're also labeled m, but this has nothing to do with the m of the spherical harmonics. So these L's are the multiple moments, but these m's actually run from 0 to 2. For m equal to 0 they describe scalar perturbations. For m equal to 1 they describe vector perturbations, and for m equal to 2 they describe tensor perturbations. So this is a tensor rank. Rank 0 is a scalar, rank 2 is a tensor perturbation. And why do I show this slide at all? Well, if you look at the vector field that behaves like an electric field, so that is curl free, you see that it couples to the magnetic field. It's time dependent. However, there is a n in front of it. So for scalars, this term is 0. Moreover, if you look at the time dependence of the B field, there is no source term, whereas the intensity is sourced by its type. So if we're looking at scalars, here we have the scalar sources. If we're looking at tensors, here we have the tensor sources. This equation, by the way, shows you that you get intensity perturbations from just tensors. The E and the B field are not sourced directly by these sources, but this quantity here, which I did not put on the screen, I think, or actually do. This quantity here actually depends on the intensity. So the E modes are sourced by the intensity, which is sourced by the sources. Now where was I going? Right, if you put m equal to 0, then the E mode cancels out of this equation. So here we only have B modes. So this is yet another confirmation of what we already knew. If you consider scalar perturbations, m equal to 0, the B modes are never sourced. These are linear perturbation equations. So at the linear level, the B modes are never sourced. Which is as much as saying that you cannot produce a vector field that has a curl when you start with scalars only. If you have vector perturbations, then m here is non-zero and here is non-zero. So vector perturbations will also produce B modes. And tensor perturbations produce B modes. For completeness, I put the source term here explicitly. And this capital H here is again confusing notation. This has nothing to do with the Hubble parameter. This capital H parameterizes the amplitude of the tensor perturbations. I didn't give the entire formulas before it. I take these from a reference that is, actually it's the reference that I gave before. It's White and Hu. It's from this reference.
Yeah. Ask a question.
Yes, please.
What? Can you explain in simple terms why the L ranks are, or the evolution of the L ranks are connected to the L-1 and L+1? Is there a reason?
Well,
or is it just comes out from
the genre polynomial?
Yeah,
it's just the hierarchy.
It's exactly. It's just hierarchy, but why is it not to -2 and +2? I don't know. So there's some mixing of anisotropy clearly because the fluid evolves, but I don't know why it's strictly -1 +1.
But I think that is just when you use when you go in Legendre space and you have the relations between the polynomials and you get such relations as mathematically.
So mathematically it comes out.
Then if we think of it physically, it's a bit more complicated.
Yeah. So I don't know the answer. Okay, so if you accept that these are the equations that describe the time independence of your polarization just before the surface of last scattering, and then the photons have their last interaction with the electron fluid and are emitted towards us, then you freeze this set of equations and you end up with your distribution of polarization of the electric type and polarization of the magnetic type. So this is not really electric and magnetic fields, it's just the fact that this is a curl-free vector field and this is a divergence-free vector field. So we've computed some quantities on the sky with a certain tensor rank, and then of course you can compute their cross-correlation in multiple space. This is very much the same like the CLs that we saw previously. If you plot that all in one figure, and you compute the power in units of microkelvin squared, because we observe a temperature, which gives the intensity of the photon fluid in Kelvin. Then here we have the temperature anisotropies. This is the same oscillatory spectrum that we've already seen many times now. But in different colors here, the lowest line, let's focus on that one first, is the autocorrelation of the E-polarization spectrum. And I already described in words that the E-polarization must be correlated with the temperature spectrum because the E-polarization has its origin directly in the temperature anisotropies at the surface of last scattering. So the E-polarization must be correlated with the temperature polarization. And you see indeed that the E-polarization peaks exactly where the temperature has a trough. And the E-polarization has a trough exactly where the temperature has a peak, etc. I won't explain why it's exactly the opposite. But at least you see that the the oscillatory shape follows exactly the oscillatory shape of the temperature perturbations. These solid lines are the theoretical predictions. The boxes are actually measurements and their error bars. So in this logarithmic plot, you see that the error bars become much smaller than the scale of plotting. This is a very old figure. By now, the e-polarization has been measured much more accurately, but you already see the peaks being observed by CMB experiments. And the cross correlation between e-polarization and t-polarization clearly is the green line. It must be non-zero, and indeed it is non-zero, because the e-polarization finds its origin in the temperature anisotropy. Okay, so this is the polarization from the surface of last scattering. And I've only focused on scalar perturbations e-polarization in this figure. What you see here is another feature that I did not yet discuss, which I will discuss now. It is an extra source of polarization in the cosmic microwave background that comes from the epoch of reionization. And it will show up both in the e-polarization and in the TE cross correlation. We've already seen this figure because it also describes how the temperature anisotropies themselves, just the scalar quantity, are affected by the reionization of the universe. But in fact, the same figure explains also very nicely why this introduces extra polarization on the cosmic microwave background. This is a 2D representation of space-time. We live in the center of the universe because we only observe redshifts, so we truly live in the center of the universe if redshift is your radial coordinate. And this outer ring is the surface of last scattering. So this is the time and distance at which the photons that we observe had their last interaction with the baryons, and they took off on their journey towards us. After last scattering, around the same time as last scattering, each electron finds its own proton partner. They bind for life, up to the point when the apocalypse comes, stars start forming and they emit very high energy radiation back into the universe, and they separate all the protons and the electrons again. It's the cosmic drama, and from this point on, the matter in the universe will be ionized again. That means that photons, when the universe is neutral, have just a very free path, but at some point the universe becomes charged again, and the photons will start interacting with the matter in the universe again. Now, at this time of reionization, if you live at this spot, and now we make this figure a little bit more complicated because now the radial direction is no longer only one time component, but if we focus just on this spot and we draw a ring around it at a constant radius, then the ring that you draw here is the surface of last scattering that you observe when you live here. When you live here at this time, you will see cosmic microwave background photons coming from these directions. Clearly, you will then see the anisotropy of the cosmic microwave background at this scale. So now if you're a charged particle, like an electron, you will have Thomson interaction with the photon fluid. So once more, you will start reflecting polarized radiation. Depending on the direction in which you're reflecting, you get the orientation of the polarization of the radiation. So if we live here, and we're looking at the CMB from this direction, we see an admixture of pure CMB anisotropy coming from this direction, plus extra photons that come from this entire circle that were reflected by the object that lives here and has Thomson scattering with these photons into our light cone. So, reionization of the universe mixes temperature anisotropies from different scales. And if you mix anisotropies, you decrease the total power of anisotropy. You're smoothing out the spectrum. But moreover, the mixing causes an extra degree of polarization. Because if light coming from here was initially unpolarized, now there is an admixture of this quadrupolar anisotropy here reflected as polarized light into our direction. And that is this bump that you see here. And this is a theoretical bump for a particular choice of the amount of chargedness of the universe between here and the time of reionization. This is the optical depth till that surface.
Measurements seem to indicate that this is not the right value.
Exactly. This value is exaggerated. This is a value too high to agree with observations. But you need it to be non-zero. Right. Yeah. So well, I went back, but I could have gone forward. You have the reionization spectrum. So here is again a theoretical plot of the same stuff: the temperature anisotropy spectrum, the E polarization autocorrelation, and the cross correlation of temperature and E polarization. And now we're going to change the parameter, that is this tau, the optical depth to reionization. And if we increase it, you see that you decrease the total anisotropy of the CMB because you're mixing anisotropies of different scales, you're making it smoother. Whereas you're increasing the E-mode polarization on large scales, because you're reflecting more and more of the quadrupolar anisotropy somewhere between us and the surface of blast scattering into our light cone in a polarized manner. And that increases the correlation between polarization and temperature. Between the polarization and the temperature spectrum of the universe. But you see that the reionization only increases polarization on large scales because at the surface of blast scattering, the anisotropies that come from the surface of blast scattering are mixed. So you decrease the power also in the polarization. Okay? So this is one source of polarization that does not come from the surface of blast scattering, but that is added to the original photon fluid on its way towards us. Okay? And now I'll talk about another source of polarization that is imprinted on the photons towards us. But before I do that, let me remind you something from the third lecture, the large-scale structure lecture. We briefly discussed, very briefly, only qualitatively, the effect of weak lensing. So in large-scale structure, you observe galaxies. These are approximately circles or ellipses with random orientations. But we observe them behind a very large cosmological structure. The photon coming from these originally randomly orientated ellipses travels through us and is lensed by the structure. And depending on the lenses along the line of sight, these circles and ellipses are squeezed into a certain direction. And the orientation of the ellipses will no longer be exactly random, but there will be a correlation on our sky. So we started with initially random orientation. The lensing of the structure produces a correlated orientation of structure to our sky. And this is for galaxies. So I hope you see where this is going. You started with random orientation and you end up with a correlated orientation. So you're adding with something that has no vector field on it. You're adding a vector field to it by mixing it with scalars along the line of sight. And also in weak lensing you have orientations of galaxies, you can decompose that into E modes and B modes and mix them. So the same effect obviously applies to the cosmic microwave background. You have a background. Let's focus for the moment only on E-mode polarized light, so the one that comes from the temperature anisotropies. The one that you get when you have pure scalar perturbations, when you only have a field of gravitational perturbations that gives rise to the temperature anisotropies. You have a background of E-mode polarized light coming from the surface of blast scattering from mostly scalar perturbations. These scalars travel through the gravitational potential, so they're squeezed and sheared towards us. Now, so far in these 2 points I only mentioned scalars. So these are scalars only, and I argue that with a scalar you can only construct a vector field from its divergence, which is curl-free. However, you have a background of scalar perturbations and E-mode polarized light that comes from the scalar perturbations, and you travel through another scalar perturbation along the line of sight. So actually here we're talking about nonlinear dynamics. We're mixing linear perturbations here with linear perturbations from here. So this is nonlinear. So this way, with a purely scalar perturbed universe, you can construct B-modes because you're adding the orientation of different scalars to the original scalars. You had an E-mode polarized light a vector field that is a divergence, you start squeezing the vector field. You start squeezing and rotating in different directions, and therefore you get also, so you change the E-mode polarization, and on top of that you add the B type of the vector field through the lensing. This is a very simple mechanism. So, if you work very hard and you measure the B-mode polarization signal, you need to take into account that this can come from CMB lensing. And that's actually been detected, and I will explain now by whom and why. Well, you know, this is the bicep 2 observations. This looks like it's an ellipse of the full sky, but this is not the full sky. This ellipse represents just a field of view of the bicep telescope that's on the South Pole. It's on the South Pole, and it looks in one particular direction of the sky. So I'm sorry that I didn't look up what the actual field of view is of bicep, but it's of the order of a few degrees. They observe the preferred orientation of CMB photons at a very high accuracy. So they have a very clear detection of the E-type polarization of the cosmic microwave background. The magnitude is given, the temperature of the fluid in those directions is given by this color scaling. And I didn't choose the color scale, but maybe the eye of bicep has something to do with the Netherlands. Of course you were thinking it's the French flag, no it's not. Moreover, they detected, as you all know by now, also B-type polarization. They were the first to detect an orientation in the polarization a polarization in the orientation of the CMB photons that is described by a vector field that has a curl, and that is divergence free. So you can even see by eye that here you have the curly pattern. And this one does not have the curly pattern. The order of magnitude is quite a bit lower. This is of the order of, so there's a factor between them of the order 10. If you look at the autocorrelation of the B-mode polarization, then the data points of the bicep satellite are these of the bicep telescope on the South Pole are these black data points with error bars. Of course, the larger the error bars grow when you go to smaller scales. And you see that there is some feature here, and there is a very clear detection that is non-zero up here. The theoretical curves, they don't really go to the data points very well, but that's not so problematic because the error bars are very large. There are two theoretical curves plotted here, and that is why I spent the last 2 slides talking about CMB lensing. The dashed curve here that goes back to 0 is the amount of beam-type polarization that you get from tensor perturbations on the surface of flat scattering. So this is the amount of beam-mode polarization that you get from gravitational waves, from gravitons that were stretched during inflation and then froze into the cosmic structure. You get this bump here for gravitational waves that have an amplitude that is about 1/10 of the scalar perturbations. But the red solid line is the amount of B-type polarization that you get from the lensing of originally E-type polarized light. So you see that it's actually a very significant fraction of the observed signal. You start with an originally only purely curl-free vector field of polarized light. You lens it, so you mix the different orientations, and you get a strong signal of beta polarization. So actually, one remarkable achievement that is not as exciting as the other one and therefore not advertised so largely is that the bicep 2 telescope has detected the strongest signal so far of B-modes coming from lensing the E-mode polarization. Now, why is it since last Friday not so clear that we should interpret this bump as tensor polarization? It is because there is yet another foreground that can give B-mode polarization of light that you observe when you look at the cosmic microwave background. And that source is dust. If you have dust particles that happen to be spinning, each particle of itself generates a magnetic field. So it has some orientation. Simply from the fact that it is spinning, you know it has an axis in its orientation. That means that the spinning dust particle will align with any present large-scale magnetic field that is there for the dust particle. And we're now considering a dust particle that lives inside the galaxy. The galaxy has a magnetic field, so the spinning dust particle will align with the magnetic field of the galaxy. This means that you have an orientation, again a vector field, entering into the dynamics. So if your dust particle happens to be emitting light, or maybe it's reflecting light, whatever the origin is, it means that you have a vector field and not a scalar field entering into the problem, and you're sourcing both E-type polarization and B-type polarization. Now, one big problem in this question is that there is no standard model of dust emission. There is, in other words, there is a lot unknown about it. There are many different theories, and there's basically a lot of theoretical uncertainty about this type of effect causing B-mode polarization. And it's because of that uncertainty that the BICEP team, with its initial claim, stated that they had detected the tensor to scalar ratio of 0.2 at many sigma. That is because of all the uncertainty about the dust polarization that they may have not taken properly into account, or in a more fair way of saying, with the knowledge they had at the time of writing the paper, they did not realize that the entire signal could come from dust. They could not realize that the entire signal could come from dust. The problem is that the BICEP telescope only measures one frequency. And if you measure a single frequency, you can of course focus on the frequency that is the most abundant in the cosmic microwave background. But the individual photons will not tell you that they come from the cosmic microwave background. You just see photons coming from that direction. If you look at one frequency, you cannot tell what the temperature of the original spectrum was. Of course, if you have a pure black body radiator, the intensity is a direct function of the temperature of the body. So in that case, you can tell what the temperature is by measuring the intensity. But if you have an admixture of sources with different temperatures at different redshifts, with different temperatures inherently in themselves, this is no longer the case, because you can, of course, you can imagine that you observe radiation at 100 gigahertz, which is the frequency at which BICEP observes. That is an admixture of different Planck spectra, different black body spectra at different redshifts coming from different objects. So only if you observe different frequencies, you can try to to separate the different origins of the photons. Oh, I swapped the S and the A. I guess it was late yesterday. And this is where the Planck satellite comes in. The Planck satellite has, as opposed to BICEP, has full sky coverage of observing the cosmic microwave background. But the benefit of the BICEP telescope is that they can observe at a much higher resolution, at a much higher sensitivity. And the Planck satellite, therefore, did not have the means to observe the B-mode polarization that the BICEP telescope observed. But they observed at many different frequencies. So you can use the Planck satellite to learn more about the dust emission of radiation that is an admixture into the cosmic microwave background radiation. And in fact, these are all data points from the Planck satellite. This is the relative power at different frequencies, or actually the cross correlation also from different frequencies on the Planck satellite, of the instruments on the Planck satellite. These numbers here are frequencies in gigahertz. And so here we have the autocorrelation of the 355 gigahertz temperature map of the sky to 17, 143, 100, etc. This is, according to the Planck team, the amount of power that doesn't come from the surface of last scattering, but that comes from dust emission, mostly from inside our own galaxy, as a function of frequency. Now
This is integrated on the sky.
Integrated on the entire sky, exactly. And now I overplot at exactly the same scales and in logarithmic in power the the black body radiation, that describes the cosmic microwave background radiation. This is actual data from the COBE satellite. You can download it and put it in your plotting program and put it in the right scales, so that's what I did. So this is really the data of the COBE satellite. Of course, the COBE satellite doesn't measure this. It is not measuring the same thing. It's not measuring the cross correlations of temperature maps. So I simply put the temperature power here at arbitrary units. The only reason I put this here is to show you what the frequency dependency is. So here we have the dust emission, which is described by a power law in this direction, and here we have the cosmic microwave background emission, which is in exactly the same frequencies, but has a different frequency dependence. Of course, if you only measure one point, you cannot tell what the relative contribution of these different two lines is. Okay, so this is an argument why you need to observe different frequencies to disentangle this line and this line. Because what you will observe is the sum of the two. The individual photons don't tell you where you come from.
Why are the three first points so?
Because, okay, so the total observation is the sum of the two, but these data points are actually not directly the temperature, but these are the temperature which the Planck team attributes to dust. So they subtracted the cosmic signal from it. So this is not a data point. This is a processed point. So I put this temperature spectrum here to give you a feeling for these frequencies, and you see that dust has a very different frequency dependence, but it is emitting in exactly the same frequencies. So you need to understand it very carefully. Now, what the Planck team observes is that the distribution on the sky of dust is very well described by a distribution that is a power law in multiple L. This is just empirically. This doesn't come from a model. This is just an observation. They see distribution of dust on our night sky, and they see that it's well described by a multiple moment dependence that is L to the power alpha. I didn't put alpha here. It's some number of order 1. They also find empirically that the temperature spectrum of the dust is given by a modified black body spectrum. This B here is the black body spectrum. Nu is the frequency, clearly. So the temperature spectrum, the temperature spectrum of the frequency spectrum of the dust radiation is given by a black body spectrum modified with a frequency to the power beta, which is given here. The dust is hence best described by a temperature of 20 Kelvin modified with frequency to the power 1.6. This is empirically. This is what the Planck satellite sees in frequency dependence of the dust emission. So this is a very different temperature from the cosmic microwave background, which is at 2.7 Kelvin. So if you observe sufficiently many frequencies, you may be able to disentangle the two.
They can be that precise in these betas and TV and what have you?
With an error bar of 0?
Well,
no, they have error bars on them. I didn't put them here. But yeah, they... Yeah, no, this is of course the reason why you can discuss endlessly whether this is correct or not. And so I say it's all empirically. Well, this really is empirically, but this frequency dependence is also how to say, motivated by theory. So, well, but if you want to fit very few data points with two numbers. Of course, it will probably be much more complicated than this, but then you need more accurate observations to test it.
We get back to the same point.
Sorry, you can?
We get back to the same thing, that we need to be more precise.
Yeah. No, absolutely. But what is very convincing and what also convinces the BICEP team about dust is that the Planck team measures that there is nowhere any deviation from this scale dependence of the dust emission, also in the patch of the sky that comes from the BICEP, that the BICEP telescope observes. And also that there's almost nowhere any deviation from this frequency dependence of the radiation coming from the dust. So it's very disappointing for the BICEP team, but what Planck observes is that the dust is seemingly very well behaved. So then if you take just the Planck observations of dust, you forget about the BICEP observations for the moment, which Planck has observed most cleanly at these high frequencies of 350 gigahertz. And you use the fact that it has this frequency dependence, then you can extrapolate the observations of the Planck team down to the frequencies at which the BICEP telescope observes. And then you get these boxes, which are error bars of the expected power as a function of multiple. So if the power in B mode polarization coming from spinning dust as a function of multiple L, observed at 350 gigahertz but extrapolated to down to 100 gigahertz, and you see that the extrapolated power actually fits very well the theoretical curve that you get if you don't know about dust, but you assume it all comes from gravitational waves on the cosmic microwave background. And you're trying to fit the same the sky at the same frequencies, 100 gigahertz. This black curve is the best fit curve. Well, it's a representative curve for the theoretical outcome of the first BICEP paper. So BICEP fits the sky at 100 and 150 gigahertz. Actually, BICEP and Keck together have 100 and 150 gigahertz. They come to the conclusion that the best fit is this tensor spectrum. Planck observes the sky at a different frequency, but has full sky access to the information, extrapolates that down to the frequencies of BICEP, and comes to the conclusion that you can attribute the entire signal to dust. It's an extrapolation at this point. This is from the paper of last autumn from Planck, the 30th paper. So then, of course, the next question is, can you observe the patch of the BICEP sky at the different frequencies with the accuracy that BICEP has in B-mode polarization, and can you really disentangle the B modes coming from spinning dust and the B modes coming from inflation? So the first step in between is what came out last Friday, and that's a combined analysis of the BICEP data of the BICEP telescope and the data from the Keck array, which is a telescope that stands next to the BICEP telescope on the South Pole. It's the same location. And you add the data of BICEP, and you add the data of the Keck array, and you add the data of Planck into one analysis. And you can compute the cross correlations of the different maps. And that is what it did this Friday. So you finally can take the data of different frequencies, cross correlate, and try to figure out if you can disentangle dust from primordial sources of B-mode polarization. And what they put in a paper of these days is the following probability distribution of the scalar to tensor ratio. So let me remind you, the scalar to tensor ratio simply tells you that what the amplitude in tensor perturbations is relative to the amplitude in scalar perturbations. And these amplitudes then are related to the amplitude of the cosmic microwave background anisotropies and to the amplitude of the B-mode polarization and the amplitude of the B-mode polarization. And you may remember from the inflation lecture that if this number is large, then the energy scale at which inflation happened is very high. If this value R is small, then the energy scale at which inflation happened is much lower. Now that they combined the data of these three experiments, they come to this final conclusion that the scalar to tensor ratio, it peaks at some value that is non-zero, but it does not exclude the value of 0. It maybe excludes it at 1 sigma, but I didn't even look up the 1 sigma values, but the 2 sigma value, or actually the 95% confidence level, because it's not a Gaussian, so you shouldn't talk in sigmas, is that the tensor scalar ratio is smaller than 0.12. And this is the most recent result. This is I guess it appeared in the archive this morning, you said? Yeah. It was already on the BICEP website yesterday and the days before. So, I hope that I explained to you what B modes are, what their origin is, and that you can produce them from lensing E modes, and you can produce them with spinning dust. I didn't show the equations for that, but I hope I convinced you that it works. And we cannot exclude that the BICEP team observed dust at an incredible accuracy. Because the dust peaks at a much higher frequency than these frequencies. So they're looking at the low frequency tail of a black body spectrum, or a modified black body spectrum. So the amount of radiation from there is much less than at different frequencies. And still in this low power tail, they observe B-mode polarization at very high significance. And it cannot be excluded that it's all dust. So therefore, unfortunately, the current conclusion is that we don't know whether there are primordial tensors in that signal that they observed. Are there questions about polarization at this point? No? Because now we're coming to...
But there is a big issue about the extrapolation and the observation of L to the power of alpha.
Yeah. Yeah, so the final word has definitely not been said about this. So it's this figure is pure extrapolation, but this data really comes from cross-correlating both maps. So you can really multiply the same patch of the sky from Planck and BICEP with each other and look at the power that you get from that Fourier transform. You see if it is not correlated or correlated, etc. The paper is a little bit short, I must say, so they don't give all the details. They don't say what they did to compute the cross-correlation and all the work that went into there. It's a very short paper. They mainly describe qualitatively what they did and come to this conclusion. So they looked at all types of cross-correlation and sources of decorrelation that they could think of that go into the analysis. Because, for example, if the Planck data at 350 gigahertz is completely uncorrelated with the BICEP data at 100 gigahertz, that would suggest that the Planck data is observing dust and the BICEP data is observing something else than dust. So that would stimulate the conclusion that the origin is tensor. So, but at the same time, the dust that you observe is something that is on scales of the galaxy. So there is a time dependence that is at time scales much smaller than the age of the universe, whereas the time dependence in the cosmic microwave background radiation, which is at scales much larger, distances much larger, the time scale going into there is much larger. So there's, at the human lifetime, no time dependence in there. So if you observe the polarization coming from dust on our sky, this may change in time. And therefore it could be that if the Planck satellite observed at a different epoch than the BICEP telescope, it could be that those two maps are uncorrelated simply because they observed dust at different times. So an absence of correlation between the two maps does not necessarily mean that BICEP observed tensors. It could mean that they observed different dust particles, basically. So this is just saying that it's a very involved, very complex matter to see whether it was dust or not. So yeah, ideally you would of course repeat the BICEP experiment with the BICEP telescope on the South Pole, but in a large range of frequencies. And of course the BICEP team has plans for the future. There's a BICEP 3 coming up, and I forgot what their frequency specifications are. But they are going to a different frequency, that's something I'm sure about. And at a higher significance, etc. So they're working on that. Okay, so now I've come to the end of all the themes that I wanted to lecture about to you. So let me briefly remind you, or maybe not so briefly, what we have talked about in the last weeks, and that is the summary of these lectures. So what have we discussed? We started out with emphasizing very much that all our observations are on the light cone. This is a space-time diagram, time in the vertical direction and space in the horizontal direction. My laser pointer is running empty. We live here at the center of our space-time. We have two eyes looking in the two directions. We observe light coming from here, light coming from here. In this space-time diagram, the light travels on lines of 45 degrees. This means that we really only have access to information on this line. We don't observe inside our light cone, we don't observe outside our light cone. Moreover, we don't observe things as a function of distance and time. We only have one line, so we have one dimension that describes the distance along this line. And in a homogeneous universe, this dimension is described by the redshift of photons. So if you had thermal radiators at different distances, all at the same temperature, we will observe them at a decreasing temperature as a function of distance, because the light has stretched more and more and more and lost more and more of its energy. The observations that we have are, for example, nearby astrophysical objects like supernovae in redshifts varying from 0 to 2. AGN and quasars can go to higher redshifts, but the highest redshift observations that we have access to on the full sky is the cosmic microwave background at redshift 1100. Given this access given the observation of information on our past light cone, and the assumption that we're not special, we come to the conclusion that the universe is dominated by different types of matter at different times. And it's described by gravity as it is described in Einstein's theory of general relativity. On the horizontal axis I put redshift here. 0 is where we live, 0 redshift, and redshift 1100 is the surface of glass scattering. On the vertical axis I put the relative abundance of dark energy, dark matter, and radiation. So the information that we have on our light cone and the assumption that the universe is homogeneous on large scales, or at least that we don't live in a special place, drives us to the conclusion that the universe at early times was dominated by radiation, later it was dominated by dust-like matter, and today is dominated by dark energy. Radiation has an energy density that scales with 1 over redshift to the 4th. Dust has an energy density that scales with 1 over redshift cubed. And dark energy has an energy density that is constant. So, whatever small amount of dark energy you put in, there will be a time at which all the other energy densities will drop below the dark energy density, and you end up with dark energy domination. The universe is best described by the Friedmann-Lemaitre metric, saying that if we don't live in a special position, the universe must be everywhere similar to here. So at first approximation, there is no space dependence, possibly a time dependence. And this space-time is invariant under rotations and translations, and from realizing this point, you can put these symmetries into Einstein's equations and you end up with an equation that gives the time dependence of the scale of the universe as a function of the energy density, the dark energy density, and the possible spatial curvature. Because if the universe is spatially closed or spatially open, there is still no special position. And if you extrapolate this model back in time, you see that there is a point in space and time where the metric is singular. And so this is the Big Bang model. Right. Next, we discussed the perturbations in this homogeneous universe. And we discussed how linear perturbations in the gravitational potential and in the matter densities grow over time into large-scale structure. The particles all fall towards the bottoms of the gravitational potential, in which large filamentary structures form. The distribution of these filamentary structures is given by the very early universe. The very early universe is described by a coupled fluid of photons and baryons, in which there is a pressure, and if you have a pressure and gravity, you have two forces acting in opposing directions, so you end up with an oscillatory distribution. A different way of looking at that is saying that after inflation, the inflaton decays into radiation and matter. It generates gravitational potentials, In each overdensity, a pressure wave goes outward through the photon baryon plasma. You can compare that with throwing rocks into a surface of water. If you throw in one rock, a nice ring will be emitted around the rock. This is like the pressure wave that comes out of the overdensity of photons and baryons. If you throw in a handful of rocks, around each rock there will be this perfect circle going around it. But if you put in sufficiently many, it looks completely random. But the random structure is given by a superposition of many of these rings. So there will be a characteristic scale in your distribution of perturbations. So the large-scale structure, the matter that falls into the gravitational potentials, falls into potentials that have this characteristic structure that is given by the baryon acoustic oscillations, the pressure waves that were emitted by the overdensities of photons and baryons. So there should be a characteristic physical scale in the distribution of galaxies and clusters. This characteristic scale is observed. If you observe a characteristic scale at different distances, you observe it under different angles. If you know the original physical size and you observe it under a certain angle, you can compute what the distance is to that object. So you have a measurement of the distances as a function of redshift in the universe. And that is exactly what the baryon acoustic oscillations give. And I hope that I convinced you that these are very clear evidence for the necessity of dark energy in describing the expansion rate of the universe, because distance as a function of redshift probes the expansion history of the universe. We observe angular scale of this feature at different redshifts, so we can infer what the distance is to that redshift. So we are probing the expansion history of the universe with baryon acoustic oscillations. Then we talked about inflation. If the universe is expanding, that means that when you look backward in time, there is a point at which the universe was singular, the Big Bang. We live here, this is our light cone, again like in the previous picture. Light travels on lines of 45 degrees in this picture. And if you go sufficiently far back in time, you reach the redshift of infinity, when the universe was infinitesimally small in size. That means that we have a horizon. We don't see any point that is right of this point. We don't see any point of space-time that is left of this point. So causality dictates that we have no access to information coming from outside of here. This is the horizon in the expanding universe. If we ask anybody who lives on our past light cone how far they can look, well, you can simply again draw lines of 45 degrees in this picture, and you see that a person living here at redshift 1100 only has access to a finite piece of space-time as well. That means that we can see observers that were causally disconnected. Moreover, if you have no knowledge about inflation and you assume that the universe has, from the initial singularity on, always been dominated by radiation, you can compute what the horizon size is at different times of the universe, and you would get to the conclusion that the cosmic microwave background, as we observe it, for example, in two opposing directions, has never been in causal contact with itself. For example, if this is the cosmic microwave background on the seen up from the North Pole, and this is the cosmic microwave background down seen from the South Pole, or up on the South Pole when you're standing upside down, then you see two patches of the sky that have never been in causal contact. Yet they have the same temperature. This is puzzling, but there's a solution to the puzzle, and that solution is called inflation. Inflation tells that after the initial singularity at redshift infinity, the universe underwent a period of accelerated expansion, which does not do strange things like pushing causality outside of the horizon, but what it does do is inflating the amount of space-time inside our past light cone. So it adds, by the accelerated expansion, it adds more and more space-time inside our past light cone, such that the horizon of these two observers, the horizons of these two observers do overlap, so they do have access to the same bit of information. In other words, inflation tells us that the entire observable universe for us, including the entire cosmic microwave background, comes from a much smaller patch of space-time initially, thanks to inflation, which blew it up to proportions that are now our full sky. So inflation brings our entire sky into causal contact with each other. Well, of course not our entire sky, because there fundamentally is still a horizon. There is still space-time beyond this point and beyond this point, which is not accessible in our past light cone. It will only be accessible to us in the future when we move up in time and our past light cone still spans 45 degrees and we can look all the way down here and all the way down there. But currently we are really out of causal contact with some patches of the universe. It's just that inflation helps to put the universe that we observe, for example at redshift 1100, into causal contact with itself. So we've discussed the fact that the universe is homogeneous and our observations on the past light cone dictate us what the ingredients of the late-time universe are. We have discussed how we observe temperature perturbations in the cosmic microwave background radiation and how we relate those to the ingredients of the universe and to the age of the universe. We have discussed how clusters of galaxies and galaxies form in a pattern that follows the same distribution as the pattern in the cosmic microwave background radiation, namely the origin of the universe comes from the baryonic oscillations. Then we have discussed how inflation helps to cause correlated structures in our entire observable universe. And today we discussed how inflation, which gives rise to tensor perturbations, which we discussed in the inflations lecture, can source a particular type of polarization on the cosmic microwave background, which has a curl and is divergence free, which is not sourced by scalar perturbations, and how that can be observed today, however, which can also be polluted with signals along the line of sight. The photons coming from the surface of less scattering can be lensed towards us, so E-mode polarization is turned into B-mode polarization. But if inflation happened at large energies, there were gravitational wave perturbations, tensor perturbations, that have an orientation, so you can produce both E-type and B-type polarization from inflation. And altogether, we come to the conclusion that the universe is described by inflation and a homogeneous metric that is filled with 68% dark energy, 26% dark matter, and 4.9% baryons, out of which only a small fraction is chemistry, the rest is hydrogen, less than 1% photons, and 0.5% neutrinos. And this is the final conclusion of these 5 lectures of cosmology, and I hope that I convinced you that this may be all wrong, but it's the best that we have at this point. Thank you very much. Other questions?
So coming back to the last statement, what is the next plausible alternative?
Right. I don't have one. Do you have one?
No.
No, but for example, the one thing that I... No, exactly. So one thing that I did not talk about, which I initially hoped to be able to talk about, but then I decided that today should be spent on polarization, is the fact that we have no access to information inside our light cone. So actually any theory that describes something on our light cone can fit the observations. So all you need to do is come up with a theory that describes the light cone. And the differences between...
One also has to assume, I'm going to say something horrible.
Yeah.
In this light cone, there is always a light cone.
There's always a light cone, yes. So?
Imagine that at some point the velocity of light is completely different.
Right. That's true. Yeah, I didn't even let go of that assumption that light is always the same velocity.
I mean, that would have consequences on many things. But
Yeah. No, so the first step that I was thinking of, which is a smaller step than what Faustina mentions, is that any model that is completely different from the standard model inside the light cone and outside the light cone could still be a fit to the observations. So there's a possibility that this assumption is the assumption of homogeneity and the fact that we don't live in a special place puts more stringent bounds on the models that you allow for than what nature did. And then the point that Fauzi makes, a model that lets go of the fact of the postulate that light is always traveling at the same velocity and that our observations are really on the light cone. If you let go of that, then Other models may be possible, of which I actually have never thought, but anything is possible then. And another thing is causality. That's a postulate, right? We cannot test causality on cosmological scales. So even if light travels on the light cone, is there anything that can exchange information on spatial separated points? In general relativity, there is not, but is anything possible there? Because if you let go of causality, then you really don't need inflation.
That's why.
Right? Except that inflation is, as a consequence, also a very nice generator of initial perturbations that are scale invariant. But actually, so inflation produces a perturbation spectrum that is close to scale invariant, but the scale invariant spectrum itself was already postulated before inflation was even invented, simply by arguments that we don't live in a black hole. So the perturbations cannot be too strong, and the argument goes also in the other direction, that if you assume that we don't live in a special time, then the future should also not become a black hole. Then you get to the conclusion that the spectrum must be scale invariant. And
it's almost all anthropic.
It's exactly, but that's exactly, that is anthropic. Now inflation is independent of your anthropic taste, gives you a scale invariant spectrum. So, but I unfortunately have no simple answer to your question like this and this model do it completely differently and also fit observations. I mean, there used to be models which I worked on that explain away dark energy by not changing anything on our light cone, but by changing stuff that is inside our light cone. Because dark energy gives accelerated expansion, but it could also be that we live in an underdensity, which means that you're changing the amount of matter inside our light cone, and that also affects the way that the stuff looks on our light cone. But these models are ruled out now, so that's a step forward. That's a step towards confirming that the standard model actually works. So now the quest is for other alternatives. I have no simple answer.
It's also amazing that the most simple explanation that works.
Yeah, that is always a very convincing argument. It's the simplest explanation.
It's amazing.
Yeah. More questions? None from you today?
Yeah, technical question that we can discuss later. It's better.
Yeah, no question that the others would benefit from as well?
I don't know, just about this R, maybe just one.
Yes.
Just, how much, do you know how much of the constraint is model dependent? I mean, I know that we can, I don't know much about that, but I know that we can relax such a constraint because there were already constraints on R before this joint analysis that were already ruling out the value measured by Bicep 2 in March 2014.
Mm-hmm.
And
yeah.
And so how can we change this constraint, or how would it work?
Yes. Because it all depends on how many parameters you're willing to put in. And actually putting in parameters means that I should just scroll. Okay. Oh, I'm now there. All the parameters that you put in are actually saying that you put all the other parameters equal to 0. The constraints that we get on tensor perturbations without beam polarization depend mostly on this picture, that the CMB temperature anisotropies can be fit by pure scalar perturbations and by a mix of scalar and tensor perturbations. But one crucial assumption that goes in there when you're trying to constrain tensors is what describes your spectrum of scalar perturbations and how many parameters do you put in there. So one simple extra parameter is the fact that the initial power spectrum is usually given by a power law, so an amplitude times k to the power ns minus 1. But if inflation was a dynamical theory, then the tilt of your spectrum will not be an exact constant, so there should be a running of the tilt. And if you allow for a small space dependence of the tilt, you already completely change the constraints on the amount of tensors, because you allow for the initial power spectrum to vary more wildly here, which means that you also allow for the tensors to be more and less abundant there. So then you increase the uncertainty on tensors. But that's just one parameter. Actually, this goes for all parameters that go into the cosmic microwave background. They all have some degree of degeneracy with each other. And parameters that are seemingly completely unrelated do have influence on each other. For example, the optical depth reionization is degenerate with many of the other parameters, including the tension to scalar ratio in the cosmic microwave pattern. Yeah. So you need what you need then is many different sources of information to combine those, and then you can try to get rid of some of these degeneracies and constraint parameters. No more questions? No?
Will you upload these talks on Indigo?
Yes, I haven't done so, but I will. So they're all recorded and put on YouTube, and so Richard actually puts the actual PDF slides in the film, so it's really readable. But I will put it on Indigo. Thanks for asking. Okay, well, thank you very much for sitting through this with me for 5 lectures.